So today we are going to start with the topic that is greedy algorithms. See, greedy algorithms, as you may have come across this name in the backtracking also when we are trying to solve the traveling salesman problem, right? So greedy algorithms, basically they are used for solving the optimization problems. We come across such kind of problems so that we are able to reduce the time complexity. Like whenever we try to solve the problem using the brute force method, like the or the branch and bound technique, the complexity of the task is very high because we have to explore each and every branch in order to find the best solution. Because if we have to explore all the branches of that particular problem, that means we have to compute all the solutions first, and then we find out that this is the best solution. Like in the case of the traveling salesman problem, when we have to find out the route with the minimum distance or the minimum cost, which covers all the cities, right? So in that case, what we have to do is we will have to compute all the routes first, and then we will say which is the route having the minimum cost, and then only we are able to get the best solution. So in that case, the problem is, like, if we have 5 cities, then it is easy to compute, right, when the number of cities are small and count. But with the increase in the size of the problem, as we have seen, because we are studying about the different kinds of data structures as well as algorithms for solving the large problems, because with the increase in the size of the input, the complexity of the problem increases, and we are working towards finding the developing the algorithms, or you can say, just give me a minute. हेलो बच्चे, बाद में 1 घंटे के बाद फोन करना. Right? So greedy algorithms helps in solving, finding out the solutions and relatively with reduced time complexity. So what do we do in the greedy algorithms is that when see the greedy algorithms we are applying all the time. So in our real life also. So when we are trying to solve any kind of problem, let's say you wanted to buy a mobile, when you have defined features, set of features, what are you are looking forward. Let's say you want to you initially you say you're looking for a mobile with you can say you have something in mind that you want to have. This should be the size of the mobile, and let's say your priority is the your camera quality. So if the camera quality you're looking for, that means all the mobile phones whose quality is less than, let's say you are looking for a mobile with 13 megapixels or greater than that. So that means all the mobiles which are having the pixel value less than that, they are already eliminated. So you can say when we are trying to buy the mobile, we have large number of Samsung is providing, your iPhones are there. So n number of companies are providing all these mobile phones. But out of these mobile phones, the ones which satisfy your requirement, so they will become the possible solutions. So they are the possible solutions. Let's say there are n possible solutions, and out of these n possible solutions, the one which is satisfying your constraint, let's say their value is greater than 13 megapixels, so you can say these are the feasible solutions. And out of these feasible solutions, you will be finding out, let's say you are looking for some other features also, and let's say you are looking for a cost factor also. If out of 5, let's say you are left with the 5 possible feasible solutions, which are the 5 mobiles which are having the pixel value, camera megapixels value greater than 13, but they are having the different prices, and you have a constraint that you cannot buy a mobile of cost more than 25,000. So that means the one which is having the cost of around 25,000, that is the final solution for solving your problem. So this is the real life problem that we solve. Then we are applying the greedy algorithms. So greedy algorithms, they take into consideration all the solutions, and then out of the possible solutions, we find out the feasible solutions, and from the feasible set of solutions, we find out the final solution which satisfy our problem. And along with, see this, see we say this is a set of solutions only when, see we are saying a potential set of solutions we are looking forward. These are the solutions which satisfy our requirement. These requirements we are specifying in the form of the constraints. So this is how these greedy algorithms, they solve help us in solving the problems. So in this particular module of greedy algorithms, we have discussed what is the basic about the greedy algorithms. Then we will be discussing about the minimum spanning trees, the graph algorithms, in which we use the greedy solution approach for solving the problems. So in the minimum spanning tree, we are going to study the two algorithms. One is the Prim's algorithm and the Kruskal algorithms, which are used for finding the minimum spanning trees with reduced time complexity. Then we are going to study about the shortest path algorithms, then fractional and zero knapsack problem, coinage problem, bin backing, job scheduling, graph coloring, right? So these are basically the various types of optimization problems where where there are certain constraints which are associated with such kind of problems, and we have to find out the solutions. These solutions, we say they are the acceptable solutions only if they satisfy the constraints which are associated with them. Otherwise, they are not the acceptable solutions. So let's move ahead with one by one. So as I told you that greedy algorithms, they are used for solving the optimization problem. And using the greedy choice property, we try to achieve the global optimal solutions by selecting the local optimal solutions. That means in order to solve the complex problem, the bigger problem, we first focus on the smaller sub problems, and then we combine their solutions in order to get the final solution. So we say for getting the best solution, what we do, we try to find out first, you can say, for finding out the global best solution, first we try to find out the local best solution. So if you can say this is based on the hypothesis that if we are getting the local based solutions, then there is a high probability that we will be, from these local based solutions, we will be able to get the global based solutions, right? So optimal substructures, you can say the optimal solution to the problem that contain optimal solutions to its sub problems. As I said, it is based on this particular hypothesis that if we have the optimal solution, optimal over here we are saying it is the best solution. Best may be depending upon the problem, whether it is the minimization problem or the maximization problem. Let us say when we talk about the traveling salesman problem, we are trying to reduce the cost, and when we say we are talking about some if a business is some company is trying to increase their sales, so they want to maximize their profit, so that is going to be the maximization problem. So given constraints, so they want to maximize their profits, and in the some cases we are trying to reduce the cost, we are trying to reduce the time, so such problems are the minimization problems. So here you can see that, as I told you, what happens in the greedy algorithm is, so we have certain set of inputs, right? So these are basically, these inputs are nothing but the small problems of the bigger problem, or you can say small set of the complete set of input for solving a particular problem. So we say initially the solution is empty, right? And for because we are talking about n solutions that we have, the n inputs, n is the size of the input. From the input size, what we are saying, we are choosing one input at a time, and then we check that whether the solution that is being obtained with this particular input, that is a feasible solution or not. If this is a feasible solution, see, feasible solution is a solution which satisfies the given constraints. If the solution is not a feasible solution, then it is discarded. If the solution is a feasible solution, then this solution is being added to the set of solutions. So here you are saying solution is equal to union of solutions of the given input. So, and finally we return the overall solution to that particular problem. So this is how your greedy algorithm works. So these greedy algorithms, they are used for solving the problems, various real life problems, and we are focusing on the graph based problems using the greedy algorithms. So here we say we are talking about the spanning trees. Spanning trees basically is used for finding a set of you can say nodes which are connected to each other. That means we are trying to create a tree from the graph that is given to us, and then see this tree covers basically all the nodes of that particular graph and without forming the cycles. So here you can say it is basically a unidirected graph and a subgraph. Here you can say one graph is given A, B, C, D, E. From this particular graph, we are creating one tree. So spanning tree is the tree which spans all the nodes of the tree uh, at least once. That means the tree should cover all the nodes of this particular graph at least once without forming any kind of cycles. So from here we can see using this particular graph we are able to create three trees. So you can create n number of trees. Only thing that you have to make sure is that this tree is covering all the nodes at least once, right? So here you can see spanning tree 1, it is covering all the nodes. Spanning tree 2, this is also covering all the nodes. So from you can start from any node and you can complete the tree. So there is no restriction on where to start. But only restriction is, so you can say this is basically the constraint. The constraint is that all the nodes, we will say a particular tree is a spanning tree for the given graph only if this tree has all the nodes of this particular graph. Only then we say this tree is a spanning tree. Then see, in the real life we basically don't have the blank graphs, we have the weight graphs. So weight graph basically represents the you can say the edge weight. So if A and C are connected to each other, then the edge weight is, you can say, 10 over here. So we get the, see, like you are working in the social networks, so you have friends on the Facebook, you have friends on the Twitter, and all the people are connected to each other in this social networks. So basically that is a graph. And when we say that me and my friend are connected to each other, then we say what is the strength of this kind of relationship. So that means when we have to compute the strength between the relationships, some kind of weight is associated with that particular relation in that particular graph. Similarly, when we are talking about the training salesman problem, we have a graph. We say we have a map. So in the map, we have the distances between the, see, all the nodes are the cities and the edges are, you can say, in the edge we may have some cost of travel or we may have the distance of travel, right? So these are basically called as the weights which are associated with these edges. So a weight graph is a graph in which edge has a weight, and the sum of weight of the graph, the total weight of the graph, is equal to sum of all the weights of all the edges. Now when we are working on these kinds of graphs, so there is a requirement of finding out the minimum spanning tree. So minimum spanning tree is, that is, we have to find out a tree. As we said, spanning tree is the one which covers all the nodes of that particular tree at least once. And we have to now find out the minimum spanning tree, that is known as MST, such that the, you can say, the tree has the minimum weight. So the tree will have the minimum weight only if its edges will have the minimum weight. So we can create multiple spanning trees from the same graph. As we said in the previous graphs, now you can see we have associated the weights with these graphs. So in the weight graph, now we have created three trees over here. So tree 1, tree 2, and tree 3. And you see each spanning tree has weight, and when we take the sum total of this tree 1 has weight is equal to 74, tree 2 has weight is equal to 71, and tree 3 has weight is equal to 72. So out of these tree, the one tree that is having the minimum weight is equal to tree 2, and this is known as the minimum spanning tree. So from the given graph we can generate n number of spanning trees, right? So the one way of finding out the minimum spanning tree from this particular graph is to create all the trees whatever possible. So you can say then after that take the minima of R, and we are able to get the tree with the, which is the MS tree for this particular graph. But this problem, so as I said, this kind of problem, this is a brute force technique where we have to generate all the possible spanning trees. So for a small graph like this, it is possible to find or create in a short span of time. But with in the real life, the graphs are not having the small number of nodes. Like if we take the if you have to create an MST of the social network graph, like of the Facebook, or you can say your Twitter, or any of the social media websites, if you see, so in that case, is it possible for you to do that particular task in a given time frame? So it may take years to do that particular task of finding of the MST from such large graphs, because in the real life, for solving the problems of different kinds of networks, we may have your nodes and edges in the thousands or millions, right? So for solving such kind of bigger problems, so what do we do? So can we have some better way of finding out the minimum spanning tree? So there are techniques, as I told you, for finding out the minimum spanning tree. They are basically the Prim's algorithm and the no, your critical algorithms. So the minimum, see, and another thing is that your from the weight graph, the minimum spanning tree that you are getting, that may not be a unique. That means you may have two minimum spanning tree, but with the same weight. So both are acceptable. You can like here it is given MST1 and MST2. Both are the acceptable solutions because their weight is same, right? So 24 plus 67 plus 2 plus 1, in both the cases here you can see, both the weight, both the minimum spanning trees are having the same weights. So that means minimum spanning tree is one in terms of the weight, because we cannot have two minimas, right? But we can have a different structure of the tree, right, with the same weight. So both the structures are acceptable because both are having the same weight. So, as I told you, like in the MST, what is the problem? We have given a connected weight undirected graph, design an algorithm that outputs a minimum spanning tree. So one way of doing that is, as we have seen, so you just generate the number of minimum spanning trees possible from the given graph. Like, and here we have to remember that the tree is acyclic. We cannot cycles if there is an edge which is forming a cycle. You have to discard that particular edge. The idea is to start with an empty graph, try to add edges one at a time, and always make sure that what is built remains acyclic, as I have just told you. And if we are sure, every time the resulting graph always is a subset of some minimum spanning tree. This is the generic approach that we apply for solving the problem. But in order to, you can say, for solving the complex problems, we have two algorithms. One is the Prim's algorithm and another one is the Kruskal algorithm. See, what do we do in the Prim's algorithm? See, in the Prim's algorithm, it is based on the idea that from the given graph, first of all, I'll show you the graph. Okay, first let us see this example. So it is, this Prim's algorithm is based on the idea that first of all, you choose the minimum edge, right? Like from this particular graph, we choose a minimum edge, and or you can start at random from any point. So and after that, all the edges that we add, they have to be adjacent to the selected edge, right? So let us say we have a graph over here, the first graph connected over here, A, B, C, D, E, F, G, right? So in this graph, first we choose any edge over here. From at random, you can choose any of the edges. And after choosing that particular edge, all the other edges that we are going to choose, they have to, let us say if we have chosen the edge AB, then all the edges that we will be covering next, that will be chosen next, they have to be adjacent to any of these two edges. Like all the edges which are adjacent to A are AB and AC, and from and if we have chosen AB as an edge, then B, E, B, D, right? So this is how we are going to choose in the Prim's algorithm. Then see, the important thing that we come across is that when we have to implement this edge, how, what is the, see, Prim's algorithm is used for finding the minimum spanning tree. And here it is based on the idea that we choose the first node or the first edge at random, and then all the other adjacent edges, they are all the other edges have to be adjacent to the previously selected edges, the nodes that we have chosen, right? And the second thing is, which is the best algorithm which can be used for implementing the Prim's algorithms. So the best way to implement the Prim's algorithm is the priority queues. Can anybody tell me what are priority queues? How do we implement them? Yes, please.
Insertion is normal, but when you have to delete from it, you can only the deletion will delete the maximum element
Okay. So how do we implement the priority queues?
using heap or
Heap. Yeah, yeah. Who can add anything else? Amisha, you want to say something? Yes, Amisha. Anybody else who can add? Who can define what are priority queues? Yes, please. Priority queues. Swati. Swati Upadhyay.
Yes, ma'am. Ma'am, we can make them with min heap.
Yes. So what is there in the main heap? What is decrease key in the main heap? Can you recall what is decrease key operation?
Ma'am, I
decrease
don't
key.
remember.
The key is set to minus infinity, and then uh, we pause to the root, and then we delete it from the menu.
See, you're talking about deletion in the priority queue, right? See, priority queues, what is the purpose of priority queues? What kind of applications do we need to create? Why do we need priority queues? Anybody? Any real life problem where we need the priority queues?
Job schedule.
Job scheduling, yes. See, for different type of task scheduling, it is required to set the priority queues, and as and when the priority changes, so that means when we say the priority has changed over a period of time, in that case, the let's say it's one task was given the priority 2 in the beginning, and later on its priority is changed to 3, so that means its value is increased. But and similarly, if some you can say if some task was given the priority 4 in the beginning, and now its priority is reduced to 1, so that means it is given high priority. So when it is easy to do this particular task with the help of heaps, right? So because when we are updating the values and then moving up and down in the tree using the heaps, the task can be done in a reasonable amount of time, right? So in the main heap we always have the minimum value at the top. Once it is, if it is removed, again the heap readjusts itself based on the various operations that we do, and the minimum value is bubbled up again, right? So the main heap is helps us in setting the priority based on the priorities. See, based on the values of the key in the heaps, right? The priorities can be set up, right? So you can say the heap can be created on the basis of the values of the key which represent the priority of a particular task. So here also, because we are going to focus, we have to find out the minimum spanning tree. That means the weights are associated with that, and we have to find out the min edge with the minimum weight at every point of time. So when we are searching for the edge with the minimum amount of minimum weight, in that case it will be easy for us to use the priority queues, which are in turn implemented using the heaps. So how to grow a tree? So start by picking up any vertex R to be the root of the tree. So we can start at random, right? So you can pick up any vertex from the graph that is given us, and that will be representing the root of the tree. While the tree does not contain all the vertices in the graph, that means because we say many spanning tree should have all the vertices. So of that particular graph, unless it is completed, we cannot stop. And find the shortest edge leaving the tree and add it to the tree. So in the spanning tree, we were just focusing on the, you can say, without considering the weights. But now, because we have to find out the minimum spanning tree, so that means weights are associated with all the edges, and the while forming the tree, we can start from any of the vertex, and after that we will keep on adding the next vertex only if the edge weight between the starting vertex and the new vertex is minimum. So, and that is, you can say, adjacent to the initial vertex that has been selected. So on the basis of that, we will be selecting a particular edge, and then we will keep on adding that edge with the minimum weight at in every iteration, and we will form the complete tree. So when we apply this particular technique, so its running outcomes, running time is O, big O, of number of vertices plus number of edges, log of number of vertices. So what do we do when we are applying the priority queue for solving this particular problem? So we choose an element R and set S is equal to R. So S is basically, you can say, it is a kind of array which is having all the all the elements which are going to be there in the spanning tree. And there we have the A, another array that is empty. So find the lightest edge. So lightest edge reflects the edge with the minimum weight, such that one endpoint is in the S and the other is in the V minus S. So in the spanning tree, see here, when we are saying we are starting creating the spanning tree, we will always start from one vertex which is chosen at random, and that is represented as the root of the tree. So that root of the tree will be part of the spanning tree, and the other vertex which are connected to this particular vertex, they are not in the spanning tree, and they will be there in the V minus S. So that means there are all the vertices minus the vertices which are there in the S. So they are there in the another array, let us say. So add this edge to A and its endpoint to S. So what we are going to do is, A is going to have the edges, and the endpoint, let us say we started with the R. So root of the tree, here you can see in this particular graph that is given over here. So here we see we have the vertices are given two colors. Some vertices are black in color and some vertices are white in color. So here we can say, when we are implementing the Prim's algorithm with the help of the priority queue, we are using another parameter, or you can say we are using one extra variable or an extra flag for of color, which help us in identifying whether this particular node or the vertex has been traversed or not. If you can say, or this particular node is spanned or not. So this color, if the color of the node is black, that means this node has already been spanned, or it is there in the spanning tree. If the color of the node is white, that means it is yet to be spanned, and then we have to see, because we have to cover, or you can say the spanning tree should have all the nodes of the graph. So in order to identify, or you can say going to that before spanning that particular vertex, we are using a color in order to identify whether this particular vertex is spanned or not. So in the step 2, if V minus S is empty, that means the from the graph we see if all the nodes, all the vertices have been spanned, then it becomes the empty. Then stop and output the minimum spanning tree SA. S will give us all the vertices and A will give us all the edges. And then if this is not empty, V minus S is not empty, then means we have to keep on iterating. So the idea is expand the current tree by adding the lightest or the shortest edge, leaving it and its endpoint. Let us now do this example, right? So here you see we have a graph. This is the connected graph that we have, and it's the weight graph. So in the step 0, what we have S. S is having, we start with the root. We have considered the root A over here, the vertex A is taken as the root, then V minus S is all the vertices except the A, right? So here you can see V minus S is having B, C, D, E, F, G. And from here we see the lightest edge which is connected to A is AB. So let us say the A was the root and the two vertices are connected to it, A to B and A to C, right? So this is the concept in the Prince algorithm, that we will be just looking at the adjacent vertices, right? So in the Kruskal algorithm, we will be choosing the edges at random only on the basis of the weight, the minimum weight edge will be created. So here in the Prince algorithm, we always create one tree, one spanning tree only. But in the case of, you can say, the Kruskal algorithm, multiple spanning trees are created. So they form a forest, and then we just connect them later on to get one spanning tree. So you have to understand the basic idea between basic idea or the basic principles of both the algorithms. So now you can see S is equal to A. So S is the spanning tree where we have started with the root A, and V minus S is all the vertices except the A, and lightest edge which is connected to, so we have two edges which are connected to A. One is AB and one is AC. And out of these, we have to select the minimum. So how do we select the minimum? We are saying we will be using the priority queue, which is will be implemented using the min heap. So we will be choosing the one edge which is having the minimum value, that is 4. So we choose the lightest edge as AB. So now in the next step, you come to the right hand side first graph. So what we have is S is equal to A, V minus S is B to G, and A is going to have the edge which has already been traversed, because we need to have the edges and the vertices both in order to create the tree. So now since the lightest edge over here is from AC and AB, that is AB, so we will put this edge in this particular A, that is the another array which keeps a track of the edges that we are following, so that we are able to create the tree. Now from this, so now S is having two vertices because we have taken the edge AB. So now S is having two vertices A and B. So A and B two vertices. So now we will be looking at all the vertices which are connected to both these vertices. And let us say which are the vertices which are connected to both A and B. AC, right? AB is already traversed. Now we look at the BC, BD, and BE. So looking at all these, here you see AC, AB, then BD, BC, and BE. Here you see, right? So once we have seen out of these, right? So AB, AC, BC, BD, and BE. See, out of these, we see BD and AC, right? Both are having the same weight. AC and BD are the lightest edge. So here you can see this particular graph. On the left hand side, first graph, the lightest edge contains two edges. One is BD and second one is AC. So from here, what we choose? We have chosen the BD. So we can choose any of these at random because both are having the same weight, right? So here in this particular case, BD is being chosen. So what do? Now we update. We have updated S, we have added the vertex D over here, and in the A, we have added another edge, that is BD. So the lightest, so in the second graph, you can see the updations that have been done. Now, again, you see what we have is, we have three nodes of the three vertices, and we have to see all the vertices adjacent to all these three vertices. So what we have is AC, then BC, then BE, then DC, and DEDF. So you have so many vertices which are connected to all these three. And out of all these, which one is minimum? That is DC, which is having a weight of 2 among all. So this is the lightest edge. So what do? We make the updates. Lightest edge is DC and we add that. So when we add that, what do we have? So S will be updated. So it will be having the value of A, B, C, D. V minus S will be reduced. So C will be removed from there. And then what we have done, we have added the CD to A. So you see on the right hand side graph. So now what we have, all the edges. So A is spanned, B is spanned, D is spanned, C is spanned. So here from here you see, if we will, A and C both are spanned, and see at every time, I just forgot to tell you that, see, once A is spanned over here, its color is not white, its color is changed to black. So that is not shown over here, but that is being shown with the help of the color. So what we can do is we can add another variable over here, that is of the color of A. So here you can see the color of A is black. Then since B was added, the color of B is black and all other vertices are white. Similarly, when D is being added, its color is changed to black, and then finally we have changed the color of C also to black. So after every iteration, as we make the updations in A, so we are making a change. Whenever we are making updates in the spanning tree, while adding the vertex, we are also changing the color of this particular vertex. So can anybody tell me which will be the next edge or the next vertex? Yes, please. Which will be the next vertex? It is shown over here. So from here you see BE. So all the vertices which are adjacent to all these vertices which are already spanned, here you can see the black ones are spanned and the white vertices are not spanned, that is in the V minus S. So in the V minus S we have E, F, G. So from here we see all the vertices, among the vertices, if you see C to F is having the minimum weight. So it is the lightest edge. So next what we will add, we add this edge into the A and the second vertex, that is F, into the S, and we convert the color of F to black. So when we after doing this operation, what do? We again find out the minimum edge. So in this case we can see the minimum edge is again F2G, which is having the weight value of 2. So we add this edge into the A, and then we add the vertex G into the S, and we change the color of G to black. So after doing this, what do we have? So we are left with only one vertex, and we see all the vertices which are going from to vertex E is B to E, D to E, and G to E, and G to E, and another is F to E. So F2 is having the minimum weight, so we select this particular edge, and then finally what we get is E is being added to the S, that is the spanning tree vertex, and this particular edge is being added to the A, and finally we are able to find the solution. We are able to find out the minimum spanning tree with by applying the Prim's algorithm and using the priority queues. So in the priority queues, what are the various data structures, or you can say we have used. So we are creating the arrays for storing all these, to keep a track of all these edges as well as the vertices, and the vertices which are spanned and the vertices which are not spanned, and also another variable to keep track of the. So we need to have an array for all the edges which will retain the color, so that we can keep a track whether the color of that particular vertex is white or black. So we finally change the color of E also black. And can you tell me what is the total weight? Yes, please. What is the total weight? What is
Ma'am,
the total weight?
17.
17.
17.
17. 17 कैसे होगा? 23 होगा. E G to
अच्छा मैम वो 6 प्लस
22.
नहीं किया. ओके.
हाँ वो नहीं, 5 ऐड करोगे. F2E ऐड होगा ना, वो अभी ब्लैक नहीं हुआ. E
ओके. यस मैम.
F2E 17 के बाद +5 करो. ठीक है. If there is any doubt how we have proceeded, any doubt you can discuss. Yes, please. If anybody is not able to understand, let me know. Okay. So Finally, what we have is our V minus S is empty. The spanning tree S is having all the vertices that we have spanned once, and A gives us all the edges. Because see, we need to keep a track of the edges because we can have multiple spanning trees, right? So the edges which we are using for spanning the various vertices, we need that in order to create the tree. So that is very important. So what did, again, if we go back to the steps, choose an element R, that was the root, we selected A over there, and then set S is equal to R. We did that, S is the spanning tree. Initially we had put A over here, and A is a set of edges. Initially that was empty. Then we find the lightest edge such that one endpoint is in S and the other is in V minus S, that we have seen through with the help of example, and add this edge to A and its other end to S, that we have been doing with the help of this particular example. So if V minus S is empty, as we have seen in the last stage, here you can see in the last graph, V minus S is empty, right? Then stop and output the minimum spanning tree, that is the solution. So S will give us all the vertices and A will give us all the edges which is required for creating the tree. So what we do, so how does the algorithm update S efficiently? We color the vertices. So there are certain questions if we come across how we are doing all these things efficiently. Initially all are white, change the color to black when the vertex is moved to S, and use color V to store the color. So we can create another variable, as I told you, we can create another array for the vertices which initially stores all the values of the color as white. You can use the letter white for W for that, and when you are updating you can update that with another character, that is B, or you can use any color of your choice. Then how does the algorithm find the lightest edge and update A efficiently? So how we are doing that, finding the lightest edge? We are using the priority queue to find the lightest edge, and we use the predict queue to update the A. So priority queues, if you can recall, it is a data structure that is implemented with the help of a heap, and it supports the various operations, which is insertion, right? We insert you with the key value in the queue, and then we have the extract min. We know using the extract min we can find out the minimum value, and then we have a decrease key, which is used to change the priorities for the new keys. So and we know priority queues can be implemented so that each operation takes O log of q, right? So all this, the priority queues we have already studied. So now we can understand how we can implement the Prim's algorithm with the help of priority queues. So here you can see this is the you can say the algorithm that we have. So here what do? We take the input as G, W is the weight, R is the root, and for each U, that is each vertex that we are taking from the set of vertices, key value of this is equal to plus infinity in the beginning, and the color is equal to W. So W represents white. So that means initially for all the key values, we have to initialize those values to plus infinity, because for finding out the minimum value, we will be comparing that with the infinity. So if any value that we will get, if it is less than this will be key value of the U of that particular vertex that will be updated. And for initially the color array contains white color. So as we update the keys, so we will be changing the color to B. So the key value of root is 0 initially, and the predict R is equal to nil. So we start at the root. So Q is equal to new priority Q. So we will, what do? We first of all create the priority queue, and we put all the vertices into this particular queue, while Q is not empty, right? So while this is not empty, what do? U is equal to Q dot extract min. So from this priority queue, what do? We are finding out the minimum value, that is the lightest edge, until all vertices in the MST. So while Q is not empty, here this indicates while all the vertices are not you can say not covered in the minimum spanning tree. So we find out the extract min, that will give us the lightest edge, and for each vertex which is adjacent to U, So here you can see U was the U is indicating the vortex that is already in the minimum spanning tree, the first vortex, and then V indicates the second one. So if the color of V is equal to white, here you can see what we are doing. We are checking the color. So if the color of V is equal to white, then that means it is not there in the MST. And along with that, if the W, the weight between an edge is less than the key value of V, so if this weight is whatever is the initial value of that key that is being assigned, if the weight of this particular edge is less than this, only then we are going to, if this condition is satisfied, because we have to find out the minimum, the lightest edge. That's why we are making a comparison of this. So key of V is equal to weight of this. So we will be updating the new value with the key. So this will help us in tracking the new weights which are being updated over there. So Q dot decrease key. So what do? We change the value. So because initial value was less, so we sorry, the greater one, because it is satisfying this condition. So we update the key value using the decrease key function of the priority queue, and then we make the new predict value is equal to Q. And after coming out of this loop, when these values have been updated, what do? The vertex has been added to the MST, and we change the color of U to black. So when the algorithm terminates, so our priority queue is empty, and the minimum spanning tree is having all the vertices as well as the edges. So the PRID pointer is defines the MST as an inverted tree rooted at OR. So this is how we implement the priority queue using, you can say, we implement the Prim's algorithm using the your priority queues. So G is how we are storing the graph. We are storing the graph. You know, we have different methods to store the graph. You have the adjacency list, adjacency matrices. Here we are using the adjacency list for storing the graph. So if n is equal to number of vertices and e is equal to number of edges, the data structure priority queue supports two operations, as we know. So it takes O log n time to extract each vertex from the queue. So done once for each vertex, it takes O n log n time, and it takes O log n time to decrease the value of the neighboring vertex. So it is also done at least once. So it takes O e log n. So the total cost that is, you can say, that occurs for implementation of the Prim's algorithm using the priority key. This is equal to O n plus e log n time. So this is the you can say, if we compare with the naive method or the generic method, this is one of we are able to do. We are able to reduce the we are able to do the task in relatively better with better time complexity. So the Kruskal algorithm for this is also used for finding the minimum spanning tree, but this we will be covering in the next lecture. So I will